All right, this is the fourth video for Unit 7, and let's talk solving trig equations. And this follows the rules of, honestly, solving any type of equation for the most part, except for the fact that sometimes we're going to have to use some trig identities, because the ultimate goal is to get down to a trig function equaling a number. So then you can either solve for the exact angles because it corresponds to a ratio we know, or we know the angle associated with that ratio, or we have to use our calculator and get a decimal approximation. Okay, so what are the strategies? Well, best case scenario, so let's go through them. Best case scenario is you have a single trig function and just solve for or isolate the single trig function. So let me give a quick example. What if we had 2 cosine x plus 1 equals 0. All right, single trig function, let's just isolate it. And when you do that, you get cosine of x equals -1/2. And let's do 2 types of solutions. Let's do the solution where you're going to give me all, and then the solution where you give me between 0 and 2 pi. So all solutions, well, cosine is negative in, I need to make sure that I'm hitting all of quadrants 2 and 3. And so the quadrant 2 angle would be 2 pi over 3. And every time I go around the circle, so every 2k pi, I'll hit that -1/2. So I could say, not cosine, dear Lord. Could say 2 pi over 3 plus 2k pi. And I also want the quadrant 3. And to hit those, I could say -2 pi over 3 plus 2k pi. So I like to do, when I'm solving for angles, when I take the cosine of getting a particular ratio, I like to do it all in one statement. But would it suffice to say 2 pi over 3 plus 2k pi and 4 pi over 3 plus 2k pi? Yes, you can say that as well. Again, I tend to like to do it in just one equation. Maybe I'm lazy about writing down too much. All right, what about between 0 and 2 pi? Well, then you would give me the quadrant 2, 2 pi over 3, and the quadrant 3, 4 pi over 3. So that would just be those 2 solutions. Okay, so that's best case scenario. Single trig function, just isolate it. Well, you could have, another way to solve is by factoring, in the sense that you factor out a common factor, or GCF. So what if we had something like this? 2 tan x sine x minus minus tan x, sorry, I had to think about this for a second, equals 0. All right, I've got more than one trig function, but I can see that both the terms I have here have a common factor of tangent of x. So I'm going to factor that out. 2 sine x minus 1 equals 0. So I'm solving for all the places where tangent is 0 and sine of x is 1/2. And let's again do all solutions versus between 0 and 2 pi. So all solutions, tangent is 0 when sine is 0, or when the y-coordinate is 0 if we're looking at the coordinate plane. So this would be every k pi. Sine is 1/2 in quadrants 1 and 2, where sine is positive. Quadrant 1 would be pi over 6 plus 2k pi. And quadrant 2 would be 5 pi over 6 plus 2k pi. And in terms of the angles, if we're just talking about 0 and 2 pi, well, for tangent being 0, it would be 0 and pi. And for sine being 1/2, it would be pi over 6 and 5 pi over 6. All right. Well, another possibility is I only have one trig function, but it is taking on a quadratic form. So let's look at something like this. So quadratic. And with that, you know, factor as you would any sort of trinomial, or if it's a binomial, or if you can think of factoring by grouping, if you have perhaps 4 terms, or you might be able, or might have to do the quadratic formula, depending, hopefully not, but all right, so let's do something like this. What if I had sine squared x minus, making something up here, minus sine x, let's see, hold on, minus, let's do minus 5 sine x plus 6. No, not plus 6. Let's do minus 6. Okay, so I notice I have a trig function that's squared and one that is not squared. So if you're not comfortable factoring or trying to factor with these trig functions, you could do a u substitution. So let u equal sine x. And then I'd have u squared minus 5u minus 6 equals 0. And this is going to factor to u minus 6, u plus 1 equals 0. So u is either 6 or u is negative 1. And don't forget, you have to plug back in, you're solving for x. So sine x is 6. Sine x equals negative 1. Can sine be 6? No, out of the range, but it can be negative 1. And so if we're finding all, it would be 3 pi over 2 plus 2k pi. And if we're finding between 0 and 2 pi, it would just be 3 pi over 2. All right, so another strategy you might need to use when solving trig equations in order to either get it in factored form or to have something you can work with that is a single trig function is to use a trig identity. So let's give an example of that. So you got to have all these kind of in your mind when you're approaching solving trig equations. Well, so what if I had, again, making something up, so we'll see how this goes. What if I had sine x plus 1 equals 2 cosine squared x? All right, well, clearly we have 2 different trig functions here, and it would be nice to have one because then I could think of employing some of the strategies we talked about earlier. So there is an identity involving cosine squared and sine squared. So I could, and remember that identity is sine squared x plus cosine squared x equals 1. And so I could replace cosine squared with 1 minus sine squared. So let's see what happens when we do that. All right, so I notice I have something squared, something that's not squared, a constant term. So let's distribute on the left side, on the right side rather, and then I'm gonna get everything to the right side. So 2 sine squared x plus sine x minus 1 equals 0. And I actually do think this is factorable. And again, if you're not comfortable factoring with sine x's, you could do a u substitution and let u equal sine x. So then you'd have 2u squared plus u minus 1 equals 0. So this is going to factor to 2u, and then plus 1 minus 1. So u is either a half or u is negative 1. So sine x is a half. Sine x equals negative 1. So again, down to what we're familiar with from the earlier problems we just did. So let's do both all and 0 to 2 pi. So for all angles, when you take the sign that you get a half, I want quadrant 1, which would be 5 pi over 6. Not 5 pi over 6, that would be quadrant 2, pi over 6. Plus 2k pi, and 5 pi over 6 plus 2k pi. And then negative 1 between 0 and 2 pi is only going to be 3 pi over 2. All right, so that's an example, again, recognizing identity so you can get a single trig function and then go from there. Another strategy we talked about, which I'm not going to go through the whole problem, but I'm just going to remind you of it because the problem was quite lengthy, just the way it turned out, was when you have two separate trig functions, yet there's no identity, I can't do any of the above strategies, but the two different trig functions do have a squared relationship. And so this is the case where, okay, so let's square both sides so then I can hopefully use an identity to make it in terms of one trig function. So the problem with this is, or not problem, or just something you have to remember when you use this strategy is whenever you square both sides, you have to check for extraneous solutions, which means when you eventually solve this problem, you're gonna have to go back and plug it into the original function to see if it in fact holds true. The left side, in fact, equals the right side when you plug in that particular value for x. So go back to the example 5 from 7.4 to if you want to practice doing this problem, or if you want to go back and see what the solution is, you can try this. Just for time's sake, I'm not going to do it right here. All right, so then the final, kind of combining all of these and thinking about all these, they all involve taking a trig function of just x. Well, what happens if you have not just x inside the trig function? So let's talk about this final thing here. And we'll do just a couple basic ones. So let's say, let me think, say I had something like this, 2 sine 2x minus root 3 equals 0. All right, so for now I'm gonna ignore the 2x and just isolate the trig function. And so I have sine of this 2x equals root 3 over 2. And often people like to, and I do recommend it as well, is maybe do a substitution. Let theta equal 2x. So at first we're solving sine theta equals root 3 over 2. And let's do this for both all and between 0 and 2 pi. Between 0 and 2 pi is trickier here, and I'll show you that in a second. But let's first do all. So we're looking for quadrant where sine's positive, quadrant 1 and 2. So theta equals pi over 3 plus 2k pi, and theta equals 5, not 5, sorry. And why am I, yeah, 5, not 5 pi over 3, sorry. 2 pi over 3 plus 2k pi. And remember though, we're solving for x, so plug back in what theta is. 2x is pi over 3 plus 2k pi, which means x is pi over 6 plus k pi. And let's do, for the quadrant 2, 2 pi over 3 plus 2k pi. So x is, if I divide by 2, I get pi over 3 plus k pi. So there are the solutions for all solutions. Now between 0 and 2 pi, remember, so I want to solve for x between 0 and 2 pi. Since I'm first going to be solving for theta, which is actually 2x, I have to go all the way out to 4 pi. So again, I'm multiplying everything in this statement by 2. The reason being is when I eventually solve for x, I'm going to divide all these angles by 2. So that's going to bring the angles between 2 pi and 4 pi to being back between 0 and 2 pi. Another way to think about it is the period of sine 2x is pi. So by the time it gets to 2 pi, it will have gone through 2 periods. So there should be double the number of answers here. All right. So again, we're solving for 2x or theta first. So, and we're back to thinking about sine of theta equals root 3 over 2. And we're going all the way out from 0 to 4 pi. So theta is pi over 3, 2 pi over 3. That's between 0 and 2 pi. And let's just add 2 pi to each of these to get between 2 pi and 4 pi. So that means adding 6 pi over 3. So I'd get 7 pi over 3. And adding 6 pi over 3 to 2 pi over 3, I get 8 pi over 3. Okay, and now remember we're solving for x. So replace theta with 2x. So I'm going to be dividing everything by 2. And hopefully we see when we do this that we're going to be, our solution should be between 0 and 2 pi. So I've got pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. And 4 pi over 3 indeed is less than 2 pi. So in some ways this can seem a little bit harder because you just have to be mindful of, again, how far you have to go out when you are putting specific angles, so that when in this case, when you divide by 2, you end up still between 0 and 2 pi. Let's do another of these. Maybe let's do one involving a calculator. That's good to go over because we haven't done that yet. So let's just say, I've done sine a lot. Let's do something different. Let's do cosine of 2x equals, let's see, negative 0.4. Or negative 2/5, same thing, but it doesn't correspond to a special ratio. We know that. All right, so we can, if you want, let theta equal 2x. So we're thinking about cosine of theta equals negative 0.4. And let's do all solutions first. So one thing to keep in mind, remember when we're talking about cosine of some angle equaling a negative ratio, we're looking for quadrants 2 and 3. So when you put inverse cosine of negative 0.4 in your calculator, and we're going to do this in radians, now that we know the range of inverse trig, we know that our calculator will give us a quadrant 2 angle. So let's figure out what that quadrant 2 angle is. And so I'm going to do it on my calculator now. So if I do inverse cosine of negative 0.4, I get 1.98. So to capture all quadrant 2 angles, I can say 1.98 plus 2k pi. And to capture all quadrant 3 angles, I can just do minus that, because negative 1.98 will land in quadrant 3. If you wanted to do a positive quadrant 3 angle, well, you'd have to first find the reference angle, which would be taking that 1.98 and subtracting pi to get the reference angle. And that would be about, sorry, I should be pi minus, the other way around. 1.98 is in quadrant 2. It should be, reference angle is going to be pi minus 1.98. Sorry about that. Because if you think about 1.98 is here, about there, so you want this reference angle. Okay, so if I do pi minus 1.98, I get 1.16. So if I want a positive quadrant 3 angle, I would do pi plus 1.16 and whatever that is plus 2k pi. Again, with cosine, I just like to do it in one statement. But it's going to be different when we talk about here, instead of all solutions, between 0 and 2 pi. And again, like before, if we're solving for x between 0 and 2 pi, that means when we first solve for theta or 2x, I'm going to be between 0 and 4 pi. So in this case, I'm going to be giving 4 angles. So 2x, which is my theta, equals, well, when we did the inverse cosine, we got 1.98. And to get the quadrant 3, remember we said the reference angle is about 1.16. So let's do on our calculators pi plus 1.16. And that gets 4.3. So those are the 2 angles between 0 and 2 pi. And let's just add 2 pi to each of those. So I'm going to do on my calculator 1.98 plus 2 pi and get 8.26. And then I'm going to do 4.3 plus 2 pi. And that's going to be 10.58 about. And so that's what theta or 2x is. And let's just divide everything by 2. So 1.98 divided by 2 would give me 0.99, about. These are all, of course, approximations here. 4.3 divided by 2 is 2.15. Then 8.26 divided by 2 is 4.13. And 10.58 divided by 2 is 5.29. And notice this last angle, indeed, the biggest angle is still between 0 and 2 pi. Okay, so lots of practice you were given in this for these this particular section. Okay, and that's it.